you for the organization, invitation, and inhibition. I'm spending 3 weeks here at NTHU, and it's a pleasure to be here, so thank you. So this talk is based on, it's actually a disaster because it will be very simple in principle, that is essentially classical field theory. And it is related to a number of questions I had about currents in the super Poincaré theories, but the supercurrent, the superconformal currents in super Poincaré theories. It is mostly based on work which I did with a master student, an excellent master student who is now doing a PhD in astronomy. And another paper which I will mention later on. So it's very simple material to start with, which I think is often ignored and should be more well known to people. It is mostly based on 1970 papers, 70 and 74 papers, by Callan, Coleman, Jacquier, which will always come under the name CCJ later on. And also the first paper of Bessumino on supersymmetry, linear supersymmetry in 4 dimensions, constructing models. And the first paper of Ferrara-Zumino on the supercurrent superfields, which is also in this period 75. And of course there have been thousands, a huge quantity of papers in between, so many that I have not read or understood all of them, and I will cite nobody, or most, I think nobody. And there is work I did which is in part related with Arnold, who was a PhD student, and Yele Arton, that's already 5 to 7 years ago. So to start with, what I will discuss is, first of all, I will consider the n equals to 0 case, that is scalar theories, because of something coming out of this simple analysis when one starts to look at the condition for scale implying conformal. Secondly, I will spend some time on the n equals to 1 case. That's the core of my discussion, looking at global superconformal symmetry, the current structures, the supercurrents, improvements, and so on. Then I will, if I still have time, but I have a place where I can stop, which makes sense, talk about putting currents of the superconformal currents into supermultiplet, which is not an obvious thing. And for instance, I will show you that in some cases you can very well have currents, supercurrents, which do not fall into supermultiplets. So when one starts to say I have a supercurrent, superfield, or supercurrent multiplets, one should be careful. There are cases where the thing just does not exist. And of course, I'm living in 4 dimensions as usual. Currents are, of course, important, essentially because quantum field theory uses them to generate Waller entities and so on. But they are ambiguous quantities, so they have this property of improvement, which makes them ambiguous. So the improvement is defined in these 2 lines here. That is to say, you can add to any current something like this, anti-symmetric, and then automatically J tilde is conserved, and the charge, which carries the physical information, the observable, is the same. Adding 1 index, which is just passive in this discussion here, would be the improvement of the energy momentum tensor by this object here. Both the fields, the currents and the tilde currents describe the same physics. In principle, they are more or less equivalent, and the question is always, is there any preferred choice, and why? Now, physics in principle will not choose, but you may have a lot of other requirements to prefer one over the others, like quantum properties, renormalization, and so on. And that is one of the parts of the discussion I will have later on. Now, the interplay between the energy momentum tensor and the dilatation current is, in principle, well known. Not by everybody, but it's well known. And that will be the starting point of my discussion. And then at the superconformal level, I will try to figure out who is in various super multiplets, current and source superfields, and so on. So let's go first to the system of Poincaré and scale, which of course is a closed algebra, right? Now, if you act on coordinates, then you get these translations from Poincaré, and then you get a dilatation down here. Just from that thing, you know that the Noether variation, that is to say, when you calculate the current, you do the on-chain variation of the Lagrangian, for instance, you will get something like this. And that immediately will tell you that you expect that the dilatation current will come out like this, such that the divergence of the dilatation current is the trace of T. Now this is wrong, or not enough sufficient, because of course fields can have their own scale variations. That is, you may add on the field themselves at the fixed value, for example, at x equals 0 of the coordinates. Obvious. That is this thing here that you can have in addition to the coordinate transformation part here. You can have a matrix of the scale dimension, which I will always call omega later on. So then you get that the dilatation current as the coordinate-related piece, which I just mentioned, but in addition there is a virial current. It's called the virial current for debated reasons, but it doesn't matter, which I could simply write in the Noether expression as taking the derivative of L respective the derivative of the fields and writing the variation omega phi of each field. Very simple. Now, the first question which was asked in the 70s, actually in 70, is can one improve T to a theta energy momentum tensor such that the corresponding improved dilatation current is x theta 2. And this is what is called the CCJ energy momentum tensor. Then, of course, the divergence of J is just given by the trace of theta. And if you have scale invariance, the theory is conformal. So for theories with scalar fields, the CCJ tensor is something different from the Belin-Fan tensor. And the Belin-Fan would be what you obtain when you introduce formally a space-time metric and take the variation with respect to the metric. And that's an object which is automatically symmetric and gauge invariant. Now, for scalar fields, the CCJ is not the Belin-Fan tensor. And these people actually showed, and it's often misinterpreted, they showed just that for renormalizable Lagrangians, and for a single scalar theory, have two derivatives, that theta mu nu exists. They don't do anything more because actually the goal of this paper in 1970 was to calculate anomalous dimensions because 70 is before asymptotic freedom, and at this time the East Coast people were looking at systematic loop calculation in gauge theories. So the purpose of that paper was not at all to discuss scale with respect to conformal, or they just were looking for scale variations induced, anomalous dimension, induced by quantum corrections. Now, starting with two real scalars, it's very easy to produce scale invariant Lagrangians which are not conformal. Very simple. An example is this. So the Z plus Z bar multiplied by DZ to Z bar. This thing is scale invariance for dimension 2/3, but it's not conformal. Usually these models are non-unitary representations of the conformal algebra, and they live in the broken phase because, for instance, here you have a metric factor, which if you want to expand the fields, you should put to a constant, breaking spontaneously scale bias. But for me, that doesn't matter because anyway, currents don't feel this phenomenon. Now, this model is Scalarian. It derives from this scalar potential, which is just Z plus Z bar cube up to a scalar transformation. And since it is Scalarian, it can be supersymmetrized. So a part of my discussion will be what happens with the superconformal current for such a scalar method, a scalar potential. Just to be complete, let's add the conformal transformation, I mean the conformal boost. Then, since, on coordinates, you add a piece here, depending on parameters of the conformal transformation, the conformal boost, which can be written like this. This parenthesis is the conformal factor of the transformation. And just from this, you expect for conformal currents, this expression here, you have a piece which goes like the dilatation current because of this. And you have a piece which will go here like this in terms of the energy momentum tensor. So this one would be correct for instance, the Bell-Infante energy momentum tensor and the corresponding real current of the figure. Now you see that if you take the divergence of the conformal, you get a piece which is just this Bell-Infante real current, and a piece which is actually the divergence of the dilatation current, and a piece which is zero for a symmetric energy momentum tensor. So if you manage to find an energy momentum tensor theta, CCJ tensor, for which d mu is equal to 0, this goes away, and then scaling variance becomes theta traceless, and that implies automatically the conservation of these currents, conform, right? Now here there is no need for specific field transformations like scale transformation of the fields or Lorentz transformation of the fields, simply because for the multiple reuse there is no such thing here. This would happen in local conformal symmetry because then you have gauge fields which have non-trivial variations under K. But for us here at the global level, we don't need to bother. Now, CCJ also found that they analyzed the question, when does such CCJ tensor exist? And they figured out that there is a condition to apply on the period current in such a way that one can, by an improvement, eliminate the period current. And what they write is the V should be a derivative of some 2-index tensor, off-shell, made of off-shell fields here. Of course, the anti-symmetric part would be a triviality, but the symmetric part is the important part here. Okay. So then in this case, as I said already earlier, you could go to a scale, to a case where that scale invariance is just the tracelessness of this theta. By the way, when you do that, the conformal currents, which I mentioned before, the concept one absorb this sigma. That is to say, if I just go back one slide, I will be left with this term here, given by d sigma here. And then I move the sigma on the left side of the equation. I define new currents k bar here, and they are conserved, and it's conformal invariance. So, two derivative scalar theories. Then we have no other choice for the sigma than to put it proportional to eta, because we know that at two derivatives, the period current has one derivative maximum, also by dimensional analysis and by just common sense. So the only symmetric tensor you can make is eta. So then you get this here. When you do that, of course, to find this combination, the condition is that you should find an F here, out of your V, and this is just to say that V is pure gauge. Curl or V must be 0 for F to exist, right? So then it's totally straightforward to analyze. Now it's not verified with, for instance, the case I showed you before. It's very straightforward to see that this is not 0, you just calculate it. or by any function, any scalar potential, which is a function of C plus sigma r. Because then in this case, the curl of my virial current is just third derivatives times Z minus sigma. So let's push the analysis a little bit further. It's very trivial. So I take a scalar model with supersymmetry to follow. That's why I'm interested in this. Then I take this Lagrangian just kinetic term, but an arbitrary metric, scalar metric, deriving from a scalar potential, okay? Then I calculate, I write down the virial current from the Newton formula. Then I analyze my pure gauge condition for the virial current. I find something like this, where all the indices here are derivatives, like here, with respect to the field and the conjugate of the fields. But this thing here is nothing else than this condition here, by integration up to a scalar transformation. So then you find that to solve your condition that V nu is pure gauge, the scalar potential must have a U1 symmetry with charges given by the assigned scale dimensions of your fields. So basically, you find at the bosonic level, nothing else, that your theory should have an R symmetry, that is a U1 symmetry of the scalar potential with charges given by the assigned scale dimensions of your fields. So this is a pretty curious result in that sense, that if you want to be conformal if you're scaling variance, the thing you need to do is just to have R symmetry before supersymmetry for n equals to 0. Km is just this derivative with respect to the fields. That's one derivative, so you do two integration of that, just using this, and eliminating some scalar transformations, you get to this point. Okay? There are three indices M here, so there should be a sum. But I guess I just forgot this one. Very simple. So now let's go superconformal. Now I want to analyze the supermultiplets of Poincaré supersymmetry under superconformal transformations. And I have the right to do that because every multiplet of Poincaré supersymmetry that we use is also a representation of the superconformal algebra. Once I have assigned scale dimensions, omega, and the U1 charges to the multiplets, to the components of the multiplets. So every Poincaré multiplet is a superconformal multiplet. Now, usually Q, the U1 charge, is constrained with respect to the scale dimension. So basically for all the multiplets that we commonly use, gauge, chiral, and so on, the chiral charges are always given in terms of omega. So at the end, the real choice is the choice of omega. Now, what is new at the superconformal level is that I have Q and S supersymmetries with this algebra for the supersymmetry. So these are the double variations, so that's the commutator of double variations. And we know very well this, that's the Poincaré, that you get a translation with an amount of translation, a vector, which is epsilon bar 2 gamma A epsilon 1. I have from time to time the mixture of indices A and B because I didn't pay attention to in my equations. But that's the same, okay? Some of them are taken from local papers and some of them are taken from global. So I just noticed now that I should have, for later on, I should have put mu here. Sorry for that. Now, so then, the rule that you get to go from Poincaré to conformal is pretty simple. You just start with your Poincaré transformation with epsilon parameter, and you replace epsilon by this spinner here, alpha epsilon plus x gamma eta, where eta will be the constant spinor parameter of the second S conformal supersymmetry. And that's the way, actually, Bessumino in '74 constructed the very first supersymmetric model. If you look at this paper, they don't do Poincaré at all, they do superconformal. Of course, if you put eta equals to 0, you go back to Poincaré. But you must add some explicit supersymmetry variations, S supersymmetry variations, to get this algebra here. And this algebra is interesting because you get in the supersymmetry algebra now dilatation together what is now the U1R symmetry of the superconformal algebra. So now T is obligatory because it's just a part of the algebra. So, again, well, actually, Best-Sumino do it more or less in this way. They start with conformal. So conformal, the variation of coordinate is a killing vector psi mu submitted to this conformal killing equation here, which has a solution in terms of the 15 parameters of the conformal algebra. Then you consider a spinor alpha, solution of the conformal killing spinor equation here. And the interest of this equation is that if you form this quantity here, then this quantity here is a killing vector. And if you go back to the algebra, you see that when you go to this construction here, you have such a product appearing in the algebra. So you start with this here, and then you verify by just starting, if you want to do it, you have to find it, but since we know super Poincaré now, you just take your super Poincaré variation and you close this algebra to reconstruct your superconformal multiplets. Now, since we need also to assign weights to some of the fields, this thing which depends on omega and q will not be generated by this phenomenon, which is essentially the superconformal variations of the coordinates, and if you want, the superspace theta coordinates. And for this, to find this explicit eta term, it's enough to produce in the double variation of Q and S, the T, T, and N term, where T and T are just replaced by omega and Q, the eigenvalues of the T and T operators, so to say. Yes. So, out of this, you can describe the supercurrent, the current structure of the superconformal algebra. So the positive one, I say nothing, because this is just the conformal currents plus the current 1R. You have two fermionic currents, and since the Q variation parameter is replaced now by this alpha with this quantity here, you certainly expect that your x mu will be given by x gamma q, such that the derivative of S is the gamma trace of S in a super Poincaré theory, where Q is of course conserved. But since there are explicit variation of it in eta, you get the supplementary term here, which I call delta S mu, which has dimension 5½ while the P mu has dimension 7½ here. So finding the form of the S mu will be simpler than the virial current traces that we have here, which are dimension 3. So this is pretty analogous with the situation of the virial current with respect to the dilatation, but now it is the S supercurrent with respect to the Q supercurrent. Okay, Q instead of T, and S instead of the virial current. So let's ask the same question. And now I will do that for an arbitrary Kähler potential. So there are a few slides here which have long formula which I will not discuss. This is just formula obtained by the component expansion of an arbitrary Kähler and an arbitrary superpotential in terms of the standard field C, psi, and F of the chiral multiplets. So I just point out some interesting terms. So first of all, the S supersymmetry term are this one here and this one here, the red one. All the black things are the same as in Poincaré, with epsilon replaced by alpha. You can see what is the role from the algebra, which I had a slide before. That is, if, for instance, I want to do this on the scalar field, when the scalar field goes with Q supersymmetry into psi, and it should return to Z to produce this term here and this term here, since D and T are a value omega. Okay, so it's pretty simple to say that when I say Q, I go up to psi, and S should go back down with a number depending on omega to produce this omega depending term. So it's this way you can get your returns here. Then, if I look at the variation of my Kähler Lagrangian, I get a bunch of terms. Now, there is one which is, first the red part is a derivative, as usual. Lagrangian transform always with a derivative. And all the alpha terms are in the derivative, and this is normal, because alpha comes always with epsilon, or epsilon comes always with alpha. And we are in a super Poincaré theory, so the epsilon terms fall into derivatives. And all the black terms are not derivatives, but they are the beta depending terms. So if you want, in a Poincaré theory, this is what violates conformal, superconformal symmetry. And to get the same thing here for the superpotential term, a derivative with the alpha term, plus a term violating superconformal symmetry, depending on beta, which is not a derivative. And if you look at these terms, you play a little bit with the black terms, you find immediately your scale conditions that W should have dimension 3, K should have dimension scale dimension 2, and then K should be asymmetric also in order for the theory to be superconformal. Not only Poincaré, but superconformal. And now you can very well violate this if you are just super Poincaré and still consider the currents. Now, supercurrents, same story. I calculate in the usual way my current. So the first one is the Q supersymmetry one. Here. And then the S supersymmetry has, as expected, an X gamma Q piece, but in addition, there is this piece here, which is my delta S mu, the analog to the period current. Now, can we improve Q to the supercurrent to Q to a new Q to eliminate this delta S? So then we can find something. We can do something like this: standard spinor improvement with gamma matrices to another Q here for some off-shell spinor psi. And it's very obvious that if we do this, the X gamma Q, which is here, will get an X gamma Q tilde plus a piece like this, just by this transformation. Then I go across the X gamma with my derivative to get this term. And when I go across, I generate a d nu X rho, which produces that term here. Now this one by itself is an improvement. It has a structure, it is an improvement. So I can drop it and just say that I can find my new S current by adjusting psi to kill the delta S term. So I choose this piece here, and that leads to the expected relation. So if you want, that is the CCJ Q such that the S, the divergence of S is the gamma trace of Q. That you can always do. There is no abstraction. It's not like a scalar where you need a U1. That is what I say. Now, this thing here, you can write in the following form. First, -1/3 omega, and then your metric, Kähler metric, times the supersymmetry variation of Z bar when you multiply psi, this epsilon by alpha bar here. Okay? Now, if the scalar potential is asymmetric, then you have this relation here, and then psi, epsilon, sorry, now is the variation of this term here. So you see that this epsilon is a component of the superfield when the scalar potential is asymmetric, because it is the supersymmetry variation of, say, the bosonic lowest component here. So you find the following results. That is, if the scalar potential is asymmetric, you can use this superfield here to improve simultaneously from what I call the natural structure, which includes the Bell-Infante tensor, an arc current for scale dimension 0, so that's never scale invariant, and two supercurrent, to new supercurrent, the CCJ tensor, and another U1L, which this time has the weight omega, the phase omega. And in this case, all currents are in supermultiplets. That is, the natural Bell-Infante structure, the left side, you will get the R current, the Q supersymmetry, the energy momentum tensor in one supercurrent superfield, which I think I will not have time to discuss. Then the virial current and the delta S mu, the supplementary term, I read it, and the improvement from T to theta, I read it from there. Since here there is no virial, no delta, and another tensor, the transformation from one to the other, which is of course reversible.
Still W is not the divergence 3.
Sorry?
In the last slide, you took the divergence of S still W. In the last slide.
Yeah, but I never asked that the T mu S mu is 0. Because I'm considering the Poincaré theory. Here I get that T mu S mu is gamma x is gamma q plus delta S mu. Here I get that T mu S tilde mu is gamma q tilde without delta S. Since I know the transformation here, delta S mu is inside it. Okay? So if you
ask the divergence 3.
No, I just consider super Poincaré theories.
Okay.
But I consider the superconformal current in a super Poincaré theory, which I have the right to do. Now the CCJ structure, of course, everything is in what would be the supercurrent superfield.
What was the gamma dot S condition which is often discussed? Irreducibility condition.
It's currents. These are currents, off-shell currents. So there is no reason to impose them. These are just off-shell currents. So first way is all-symmetric, standard case. That's the case that everybody has more or less the feeling. Now the case if I'm super Poincaré, but I'm not asymmetric, the scalar potential is not asymmetric. Like the scalar potential I showed you before, this little example with one complex field. Then in this case, the CCJ tensor does not exist, but the improved S current exists. And as I told you, the difference between the S current and the improved S tilde current is not a variation of anything. So it's not in a supermultiplet. So that is to say that the improved supercurrents which exist are not in a supermultiplet of currents. So that's a case in which the statement that supercurrents or currents of the superconformal algebra, the statement that they would assemble in supermultiplet or superfields is just false. And then of course you have a case where K is scale invariant, but not necessarily asymmetrical. So then you go to what is called the Ferrara-Hatzungen structure. And W is never involved in all this discussion. That is, you can always break or not break with W. So that's the point I said I could stop. The next slides, which I will not show except for in 1 second, this was just to put in picture, so to say, this question of supercurrent structure, supercurrents of superfields, that many of you should know. But anyway, my point was to essentially emphasize two things which are related to the role of U1 asymmetry. First of all, if you look at scale implying conformal, this U1 asymmetry is already present in the n equals to 0 scalar theory. Nothing happens for fermion and gauge fields because you don't need this improvement. Actually, the CCJ tensor is the Belling-founded tensor. Second thing is that at the level of n equals to 1, you have a distinction which depends on if or if not the Kähler potential as an asymmetry concerning the situation of going from the Belling-founded structure, which always exists, to another one which you may like or not. So, thank you.
Any question? Yes.
It's not a question, but it's just a comment. But have you studied my paper on the
Look, I'm not claiming I did all that. I said in the beginning.
You said that you worked with your former students, master students. Are you going to publish a paper on this subject?
No.
No?
No, no.
Is it published or is it?
No, no, no. No, no, the only thing which is published is the paper on the supercurrent structure, which is something else with Ardong and something. With Yele and Arnold. So I'm not, it's not my intention to claim that I did this without referring to the literature, okay? I just did this because I think people should know that better. And also there are little things which are different from the usual thing that people say.
Some time ago, and I forgot what I did in my paper, but I studied. I mean, probably in the slide you just flashed, you studied the structure of the supercurrent with scale symmetry without R symmetry, or are you going to?
Yeah, but this you did, no?
I thought I did some related thing, but I'm not sure whether it is completely.
I can tell you when I started to be interested in this is that because I was discussing with people I will not mention by name who have published lots of papers.
Yeah.
And they were making a number of statements. You know, there was this long controversy on what scale implies or does not imply at the quantum level. And I realized that a number of these very simple classical, so to say, field theory arguments were unknown to them. So for instance, showing them that a little single complex scalar model can be scaled by not conformal was surprising them a lot. So I started to be just involved in this. And today I decided just to give, so to say, a lecture on this.
Another related question is, have you studied the supergravity version or superconformal?
Yes, in part.
In part.
Yeah.
And what is your conclusion? I was interested in the, well, if you have R symmetry, without conformal symmetry, you can use new supergravity. And in most generic situation, you can just use, there are no supergravity. And I was wondering whether you can do the supergravity version for the scaling variance without R symmetry or something.
Yeah. Yes.
Do you have any thought on it?
Well, I'm working on similar things. We can talk, but I don't have results. I have something like 60 pages of calculation on this.
Any other question which is more closely related to the topic?
No, it is related. I understand it's not so close.
Okay, if not, let's thank us.